Hello, my name is Sean Fitzgibbon and welcome to this video in which I'll give you an introduction to a technique called Tract-Based Spatial Statistics or TBSS. In the earlier video on diffusion tensor imaging, we saw how we can derive some scalar measures from diffusion images such as FA and MD. So the question is, what do we want to do with these measures? And typically, we want to compare them across subjects. That is, to correlate them with something like disease severity, or compare them between different groups, like disease versus control groups, etc. When comparing such maps between groups, we have to take care that the images are well aligned between subjects, so that we are comparing like with like. This alignment is made difficult because each subject's brain is shaped slightly differently. The standard approach for this is to warp each subject's image to align with some standard brain image using nonlinear registration. Once the brain images are aligned, you can then compare the FA in each voxel between the groups. While this approach works well for most MRI images, diffusion MRI images have the problem that there are very sharp boundaries at the edges between white matter and grey matter or CSF. If, after registration, there is some residual misalignment, which there always is, this might lead to false positives in the voxels close to the edge of the white matter as illustrated here. TBSS is a tool that proposes to solve this problem by only comparing the FA in voxels at the center of the white matter, far away from the boundaries. This center of the white matter is often referred to as the white matter skeleton. By only considering these voxels, it avoids the false positives shown on the previous slide. TBSS defines this white matter skeleton first on a mean FA image by finding the local peak FA in specific directions. This is what the skeleton looks like in 3D. Surprisingly, it is less tubular than you might expect, but rather tracks appear to be more like sheets. Due to the different brain shapes between people, this skeleton derived on the average FA will not align perfectly across subjects. This residual misalignment is what we're going to deal with now. The problem of misalignment is solved at the single subject level. For each subject's aligned FA, for each voxel in the skeleton, in red, we move perpendicular to the skeleton, indicated by the blue arrows, and search for the peak FA value, which we then sample as the value for this location in the skeleton. This should be the value for the center of the tract. So now we have a center of the tract correspondence for each voxel in the skeleton across subjects. And this shows how we do that with a number of different subjects. To reiterate, for each voxel in the skeleton, for each subject, the value of the voxel will be the peak FA from that subject perpendicular to the skeleton. Thus, we can simply feed these into a general linear model using the same machinery that you have heard about already and do voxelwise statistics. And this approach has been very successful in a number of applications. In this example, we have mean FA in healthy controls and schizophrenics. If we do TBSS, you can see that there are some regions here where you can see a difference in FA between the healthy controls and schizophrenics in the corpus callosum and in the fornix. And TBSS is not restricted to FA. Once the skeleton is created, other diffusion metrics can be sampled as well. In this multiple sclerosis example, there is a difference in FA in the top left and a correlation with lesions in the upper middle and with disease scores in the upper right. Below that, we have measures of axial diffusivity, the diffusion along the principal axis of diffusion, and radial diffusivity, the diffusion perpendicular to the principal axis. And you can see the axial diffusivity is largely unchanged. Thus, the FA differences seem to come from a difference in radial diffusivity, which suggests demyelination. The water molecules can more easily diffuse perpendicular to these axons because the myelin is no longer hindering it. So in conclusion, TBSS is a method that allows you to compare different scalar metrics across subjects and groups. It attempts to solve issues with aligning voxels across subjects. It allows you to do whole brain analysis, and it is simpler than many other approaches such as tractography-based methods.